Hello and welcome to part 2 of the video series on vector analysis. Our first topic is the dot product between any two vectors. It is an important topic as it tells us how these two vectors align or how much do they overlap. It also gives the information about the angle between the two vectors, and we can find the projection of vector A onto vector B using the dot product. The dot product between the two vectors is given by the following formula. The cosine term in this formula is a representation of percentage of alignment between these two vectors. This means that when theta is equal to 0, two vectors are fully aligned or parallel, whereas when theta is equal to 90 degrees, two vectors have zero alignment or they are both perpendicular to each other. This leads to another important result, that the dot product of a unit vector with itself is equal to 1, whereas the dot product of a unit vector with another unit vector that is perpendicular to it is equal to 0. Based on this, we can write the dot product between the two vectors as a sum of the product of their components. Here we have also used the summation notation to express this sum. As we can see, the output of the dot product is a scalar quantity. Therefore, the dot product is also known as the scalar product. Now, let's look at the projections. There is a scalar projection and a vector projection. Scalar projection is considered the length of the segment of a vector A that lies on the line in the direction of vector B. Vector projection, on the other hand, is a vector in the direction of B with a magnitude equal to the scalar projection of vector A onto vector B. It is essentially the vector shadow of A when light is shown from B. Another important topic is direction cosines. These help us understand the orientation of a line or a vector in three-dimensional space. These are cosine of angles which a vector makes with the coordinate axis. Now in the previous slide, we saw that the scalar projection of a vector onto x-axis will be the dot product of the vector with the I-unit vector. And from there, we can extract cosine of alpha as the dot product between the unit vector of A and I-unit vector, which is also equal to the dot product between the vector A and the I-unit vector divided by the magnitude of vector A, and which can also be written as component of vector A in the x direction divided by the magnitude of vector A. Similarly, we can obtain the relation for cosine beta and cosine gamma terms. This also leads to the following identity, which ensures that the direction cosines correspond to a valid orientation in the 3D space. Therefore, given direction cosines, we can construct a unit vector that points in the same direction as the original vector. Now let's look at the cross product of any two vectors. The cross product of two vectors results in another vector that is perpendicular to the plane of both the original vectors. Therefore, this product is also known as a vector product. The direction of the output vector is determined by the right-hand rule. We can also see that B cross A is not equal to A cross B. Instead, it is equal to negative of A cross B, which means that this vector has an opposite direction. The magnitude of the cross product equals the area of the parallelogram with the vectors A and B for its sides. The formula for the cross product of vectors A and B is given as follows. In this formula, U hat is a unit vector perpendicular to the plane containing the vectors A and B. And as I said before, its direction is determined by the right-hand rule. This also tells us that when theta is 0 or when the vectors are parallel, their cross product becomes 0. Another way of writing the cross product is as follows. We can also write the cross product in this form. Now let's try to write some code in Python to solve some scalar and vector product problems. The first problem that we will solve requires finding the dot product and the angle between any two vectors. In this example, the vectors are 2i hat minus j hat and 3i hat plus j hat. Although NumPy library has a function called dot that computes the dot product of two vectors, but we'll write this dot underscore product function where we are computing the dot product by taking the sum of the element-wise products of these two vectors. Then we call this dot underscore product function and also verify the result using the dot function from the NumPy library. In both cases, the result is equal to 5. In the previous slides, we have seen that cosine of angle is equal to the dot product divided by the product of magnitudes of these two vectors. So we compute the angle using this and convert it to degrees, and the result is 45 degrees. Now in the second example, we'll try to find the projection of A onto B for the vectors used in the previous example. For this, we write the vector projection function, which takes two vectors as arguments. In the previous slides, we have seen that the scalar projection of vector A onto vector B is simply the dot product between the vector A and the unit vector in the B direction. And the vector projection is simply the B unit vector scaled by the scalar projection. Then we call this function and we see that the scalar projection is equal to 1.6, whereas the vector projection is shown in the figure as the red vector. Now let's try to find the cross product between the two unit vectors, one in the x direction and one in the y direction. For this, we write the cross underscore product function and calculate the cross product using the formula from the previous slides. There is also a NumPy cross method that we can use for this task. We'll call both methods and see that they both output the same answer, which also validates the code we have written. And the answer is another vector in the z direction, that is 0, 0, 1. There is also another important result that we see is that the cross product between I unit vector and j unit vector produces the k unit vector, which is orthogonal to the plane containing I unit vector and j unit vector. We can also see that the cross product of the I unit vector with itself is equal to 0. Now let's see how we can compute triple products like these. In the first expression, we see that the dot product will produce a scalar value, but then we will multiply a scalar with a vector and the output will be a vector. In the second expression, the cross product will result in a vector, and then the dot product of two vectors is a scalar, so the output of this expression is a scalar value. Another importance of this expression is that this gives us the volume of a parallelopiped whose three sides are vectors A, B, and C. In the third expression, two cross products will output a vector. The last expression is also equal to B times A dot C minus C times A dot B. Another important result that we can derive from the second expression is that the expression is equal to 0 for coplanar vectors. If we look at this expression, if B and C are coplanars, their cross product will produce a perpendicular vector, and if A is coplanar with vectors B and C, then its dot product with an orthogonal vector will be equal to 0. We can now write a function to compute the scalar triple product for these three vectors. For this example, we can see that the answer for the scalar triple product is equal to 4. With this, we conclude our video. In the next video, we'll learn about another important topic, that is vector differentiation. Please subscribe to my channel for more videos like this. Thanks for watching and see you in the next video.